In this video, we will briefly review techniques for feature visualization. In contrast to the saliency masking techniques, these approaches seek to engineer images from a starting point of random noise in order to create something which maximally activates some component of the network. Where here we can choose to optimize against the activations of a single neuron, or a group of neurons, or a channel, or a whole layer, or compare against the output probabilities or class logits. Moving on to specific examples of feature visualization, the first technique I'd like to talk about is layer visualization through gradient ascent, proposed by Erhan et al. In 2009. So the idea here is that one updates the input iteratively so as to maximally activate a specific layer of the network by maximizing the amplitude of the activation maps which are generated. Thus, the optimization is very similar to standard ConvNet optimization, except that this time the weights are fixed and instead the input is updated through taking steps in the direction of the partial derivative of the activation maps differentiated with respect to the inputs x. This was then adapted in this 2013 paper by adding regularization so as to remove at least some of the high frequency noise that would otherwise be generated. And the other difference of this paper relative to the previous one is that it was specifically focused on optimizing against the output of the logits layer. So looking at the classification nodes, but specifically the logits rather than the softmax, where the logits are the outputs before they're pushed through the sigmoid or softmax. This is because it's regularly been observed that this happens to work a lot better than using the softmax output, probably because softmax can be optimized by minimizing the scores of other classes, which is not what we actually want. But generally, it's regularly observed that feature visualization simply doesn't work well without regularization. Without it, the result becomes dominated by high spatial frequency noise and these repeated patterns that you can see down here. It's thought that whatever causes this is probably akin to whatever is making the networks vulnerable to adversarial attack. So various different approaches for regularization have been proposed, not just L2 regularization, but other options including minimization of total variation, where total variation represents the integral of the absolute value of the gradient, and where this is going to be high for high spatial frequencies. Thus, minimizing it tends to encourage generation of piecewise smooth images, for example, as shown on the right. Another option is to instead repeatedly Gaussian blur the output during training, or to perform clipping, so either to set pixels with small intensity norm to 0, or pixels with a small gradient to 0. This is because even non-salient parts of images tend to show small non-zero values, generally because the gradient itself typically is non-zero everywhere. So by clipping these small values, it can improve the specificity of the result. However, if you can't get rid of these high spatial frequency patterns, why not just use them to create psychedelic images? For example, the deep dream visualizations that some of you may have seen previously work by simply applying this layer visualization, but instead of giving the network random noise, they give it a real image to optimize on top of. And then style transfer takes this one step further to use CNN features to extract image style and content, and then uses this to fuse the style of artworks with the content of photographs. For example, to extract just the content, it's possible to optimize a loss which seeks to minimize the difference between the activations from a real image and a white noise image optimized to resemble the content of that image for a specific layer of the network. Then the style of an image can be returned by instead optimizing a white noise image until the inner product of its activations more closely represent the inner product of those for the original artwork across all layers up to some layer L. And by jointly optimizing these, it's then possible to create these new images which fuse the style and content into a single output. So, in summary, instead of looking at which features of a specific image are important for correct classification of its label, we can instead try to create images which explain what a specific channel or layer is focusing on. And we can achieve this by optimizing an image which starts with random noise until these activations become maximized, However, if we do this on its own, it typically generates visualizations with lots of high spatial frequency repetitions or noise. This can be reduced to an extent through regularization approaches such as L2 and total variation penalties or smoothing. However, in my opinion, these types of visualization are more difficult to interpret than saliency maps. They predominantly seem to have contributed more to artistic endeavours such as style transfer, more so than model interpretation. It nevertheless pays to be aware of them, but I've seen no examples of their use in the medical domain.